Thank you, Paolo. First, let me thank everybody who makes this workshop possible. I'm really happy to be back after a quite long time of online seminars, so this feels really good. Yeah. Okay, Levi-Civita connections in non-commutative differential geometry. So what I want to do here is give you a quick overlook of what has been done, things that, problems that still have to be solved, and yes, then at the end I will also hint on some paper that I'm writing with Paolo, and we couldn't really finish it in time for this meeting here, so I can just give you some hints, but yeah. Let's see. Okay, so something that all of you know. So we have this fundamental theorem that on every pseudo-Riemannian manifold, there's one and only one Levi-Civita connection, meaning that this is a connection on the manifold which is vanishing on the metric, and it's torsion-free. And of course, what we would like to do is would like to be slightly more or much more general. Okay, first of all, you know this is a very important tool for GR, and what we would like to do is generalize this to non-commutative spacetimes. Okay, so what this would mean is we would have to replace the smooth manifold M by a non-commutative algebra that we think of as function on some kind of non-commutative spacetime M and C. And of course, there are some problems. First of all, we would have to know what a differential calculus on such an algebra is. We would have to know what vector fields are, what connections, their torsion and curvature is, and also what are metrics and metric compatibility of a metric with a connection. And it turns out that most of those questions are pretty well known. Like it's clear what a differential calculus is, what vector fields are and connections are. But for the last one, sorry, I can take the mask off. That's a good point. I'm so used to simply wear it. I was not even realizing that I was still wearing it. Okay, now it's much better actually. Okay, so the first 3 points, they are pretty clear. So even on a very general algebra, it's known what a differential calculus, vector fields, connections are. And this is known stuff that I will tell you anyway about. And the last point is not that clear. So it's there are several ways to think about metrics and metric compatibility. So this will be one of the main points I want to talk about here. So let's look at some history. Yes, so since this workshop is dedicated to John, I think it's definitely worth mentioning that he was working in this field. So on fuzzy spaces, he gave the notion of what a differential calculus is, what a Riemann tensor is, and in this settings, the metric was always a central one, meaning it's the same if you multiply a function from the left or from the right. AG equals GA. And yeah, this is the setting, and he was working on this in the 90s even, so pretty early. Then there's the very well-known quantum Riemann geometry of Bex and Majid. And I'm not sure if you heard so some of you might have heard the talk of Shan in the previous week, where he was also talking on this topic. And yeah, it's a very well studied field. So there are examples that are pretty nice. And again, here we have to work with central metrics, yeah, and bimodule connections. So bimodule connections have some kind of two Leibniz rules. I will tell you about this later. There's a notion of tame differential calculi, and Gianni, I think he's in the audience, so yeah, here. So there are also people working on things called tame differential calculi, and they are pretty close to central differential calculi in a sense that the modules are really close to central ones. And so again, we see here that there's the word central appearing. But here we can prove, they can prove some nice theorems in the sense that they have a Levi-Civita connection for a quite broad class of examples. There are the matrix quantum groups, and Heckenberger and Schmidtgen classified all the bicovariant differential calculi there. And so it was also possible to say what Levi-Civita connections are. And they also proved that there's just one and only one Levi-Civita connection on those matrix quantum groups. And there's more recent work of Bomik with his student. And yeah, they are taking some of the notions of Heckenberger, Schmidtgen, and they try to push them a little further. And so also there, they can prove there's one and only one Levi-Civita connection, but here they need invariant metrics and connections. And lastly, let me mention also the work of Arnlind, because he will be then the next speaker. So he will tell you something about pseudo Riemann calculi and Levi-Civita connections with some kind of frame of derivations there. But yeah, this will be part of the next talk. So many approaches to think about metrics and many ways to solve it, but the message is in most of them we cannot take a general metric, but rather a central one. Yeah. So in most of those, you can see the metric has to be a central one, and of course we would like to be a little bit more general in the sense that yeah, we don't want to have this, but what about just looking at general metrics? And there are some ways on how to approach this. For example, in a paper by Wess and others, they introduced Drinfeld twist deformation quantization of Riemannian geometry. And here they don't need central metrics. And yeah, it turned out that also here you can prove a Levi-Civita theorem, yeah, which was also proven by Paulo. And so the goal of this talk is to extend this Drinfeld twist setting to triangular algebras, which correspond to symmetric monoidal categories. Yeah? And so this might sound scary, but this is a really huge class of examples. In a sense, here we are having Drinfeld twist deformation quantization. We have super symmetric algebras. We have Sweetless-Hopf algebra and the corresponding module algebras. So yeah, it's a very broad class. So this is what I want to do in this talk in the remaining minutes. And yeah, so you can find all of this in two papers. The first one is one of mine, and the second one by Paulo. And it actually turned out that we both were working on the same problem. I was just a little bit faster in proving it, but I was just proving it for a smaller class of metrics. So Paulo somehow finished this, finished the full proof. Yeah. Okay, so the plan of the talk is first a quite general introduction to first order differential calculi. Then I would like to advertise a little bit the braided Cartan calculus, which is the first step we need if you want to talk about Levi-Civita connections. Huh? Then secondly, thirdly, sorry, braided Riemannian geometry. And lastly, maybe in the last slide, I can hint a little bit on current work of Paolo and mine. Yeah. Okay, so probably many of you know this, so probably I can go here fast. So every module I'm looking at will be a module over a commutative unital ring. So you can think of the real numbers, complex numbers, or the formal power series. So we also have deformation quantization here. And take A to be any associative unital algebra. And definition, going back to Voronowicz, maybe even further back, says that a first order differential calculus on such an algebra is a tuple gamma d, where gamma is an A by module and D is a K linear map satisfying a Leibniz rule such that gamma is spanned by A and dA. So that's very basic. We don't need anything. This works on an algebra A. In a similar way, you can say what a higher order differential calculus is. So this is now just a differential graded algebra that starts with the algebra A, such that in every order, this is spanned by wedges of D. And okay, I also need this notion that from the product of such a differential graded algebra, this gives me a kind of map from the tensor product of two forms to m plus n forms, but that's clear. Yeah. Let's have some quick examples. So, of course, classical differential geometry is one. So here we have our algebra is now just functions on a smooth manifold. Our forms are just sections of the cotangent bundle. D is the RAM differential, and you know that there's this local form. So this just means that gamma is spanned by A and dA locally. Second example, maybe I can skip this. So, for example, here, yeah, let me skip this because of time reasons. Famous example, the quantum plane by Wess and Tsumino. And one thing that you can say that for any algebra A, you can find a first order differential calculus by just looking at the kernel of the multiplication map. And the differential here is given by just 1 tensor A minus A tensor 1. You can prove this is a first order differential calculus on A. And actually, every other first order differential calculus is a quotient of this calculus. We don't really need this, but I just think it's a very nice theorem. Yeah. Okay, connections in this setting are also very simple. So just fix a higher order differential calculus. And then we say that a right connection is just a K linear map from gamma into the tensor product of gamma over A, satisfying this Leibniz rule. And you can check that this gives back the classical definition. If you just pair this with a vector field, you will see this is just the notion of connection that you know from differential geometry. We can say what torsion is in this case. This is simply given by this simple form. So just nabla concatenated with the wedge product plus D, which gives you a map here from gamma into the second wedge product. And also curvature, very simple, just the square of nabla, where here this nabla dot have to define. This nabla dot is given by this formula here. Yeah, just something you can write down, and it's a nice exercise to check that torsion and curvature are right A linear maps. So they correspond to tensors, you can say. Okay, this was the general introduction now to braided symmetric differential geometry. Yes, and this is nothing I came up with. This is much, much older. So probably the first reference is some lecture notes of Manin. Also, other people later on studied this. And so the message is to take a symmetric monoidal category. This is nothing creepy. This just means you have objects here, and you can tensor them with a tensor product. You can just think of the tensor product of modules or that you know. And then we have this operation sigma, which is an isomorphism in C that tells you how to flip two objects M and N. And we just need those three properties. First of all, those two, the so-called hexagon relations. And this just means that if you flip the tensor product M tensor N with an object O, this is the same as first flipping N and O, and afterwards M and O. So also something very natural. And lastly, we want the sigma squares to the identity. And then this is called a symmetric braiding. And there's the meta theorem of braided symmetric differential geometry, saying that differential geometry is transferable to a symmetric monoidal category if one uses this this rule here. And the rule is that every time when you flip two objects, you actually braid them. Yeah? So yes, that's the meta theorem, and I will show you now with the braided Cartan calculus how this works. First of all, the main class of examples for symmetric monoidal categories is the following. It's the left modules of a triangular Hopf algebra. So left modules means there's a left action, and morphisms are left linear maps. And on the tensor product of two modules, we just act with the co-product of our Hopf algebra. And the corresponding braiding operator is given by the flip operator, and then afterwards by the action of the inverse of R. And just as a quick reminder, let me tell you what a triangular structure is. So this is an element in the tensor product of the Hopf algebra with inverse given by the tensor flip, such that it intertwines the coproduct with the flipped coproduct, and such that the hexagons relations here are satisfied. And okay, this is just a Hopf algebraic way to phrase what the axioms of a symmetric monoidal categories are, because you can prove that this here, this sigma R is a symmetric braiding if and only if R is a triangular structure. And so here, again, I want to stress that this is a quite huge class. So Grünfeld twist, deformation, quantization is of this type. So we have the Moyal-Weil star product. We have all kinds of twists. Yeah. And let me also stress that maybe some of you saw the talk of Richard Szabo on Sunday, I think. Yeah. So and so he is exactly working in this setting. So he is also for a triangular Hopf algebra. He looks at left edge modules, and then uses the meta theorem that I showed you to say, for example, what L infinity algebras are in this category, and then formulate some field theory, just by this meta theorem. And yeah, so this should just stress that this is something quite useful. Okay, so fix a triangular Hopf algebra and take a commutative algebra object in this category. So this means I have an associative unital algebra such that the product is left linear, or stated otherwise, the product is compatible with the Hopf algebra action. This is just stated here. H1 and H2 is the coproduct of H. So if I act on the product, it's just the action of the coproduct. And I don't have commutativity, but I have something which is pretty close to commutativity, namely braided commutativity. So BA does not equal to AB, but it equals the action of R on AB. Yeah? And so then this is called a braided commutative H-module algebra. I can do the same thing with a commutative A bimodule object. So this would mean that M is now a bimodule. The A module actions are compatible with the H action. Like, okay, this is what this line here means. And I don't have commutativity, but braided commutativity. So A times M is not equal MA, but I need the correction by the action of R. And this is called a braided symmetric H equivariant A bimodule. So here in this setting, we can do differential geometry pretty easy and very parallel to classical geometry. So everything works. And let me just outline this quickly. I would start with vector fields here. So my first definition is this here. I say braided derivations are just endomorphisms on A that satisfy a braided Leibniz rule. So here, okay, x of A, B is not x of A, B, A, x, B, but I have this term here, which is different. And the reason is that I'm in this term, the order is spoiled. So I can see it's always XAB, XAB, but here it's AXB, so that's why I have to braid A and X. And it turns out that this X here, this has some nice properties, namely this is a braided symmetric H equivariant A bimodule if I choose this bimodule action, and it's furthermore a braided Lie algebra with respect to the braided commutator. And braided Lie algebra just means this, that it satisfies all the properties of a classical Lie algebra, just with some braidings every time two objects are flipped. And in other words, this is just a Lie algebra object in our braided monoidal category. Forms are now just dual to vector fields. I take left, so I take gamma to be left linear maps from vector fields to A, because I would like to have a pairing with vector fields being on the left. If I would like them on the right, I would have to choose right linear maps. I can get a differential by just this simple definition here, x of dA equals x of A. And then just from the simple properties, I can prove that the Leibniz rule holds and that the H action intertwines D, or D is invariant under the H action. Under some technical assumptions, it follows that gamma D is a first order differential calculus, and I can get an insertion operator and a Lie, the derivative, by the braided commutator here, or braided commutator. And okay, they satisfy the properties we know from classical differential geometry just with a braiding here, because again we can see that the order is spoiled in the last time. It's x omega eta, omega x eta. That's why we need a braiding here. Okay, then this gives us the braided symmetric Cartan calculus, meaning that I have all these compatibilities of the structure maps. So here this even works for multi-vector fields. I didn't tell you how this works, but you can make sense of a Schouten bracket also in this braided setting, and then this is the Cartan calculus, and as a special case you get the classical Cartan calculus and also the twisted Cartan calculus that was already known from the paper of Wess. Okay, now since I'm running out of time, now coming to Riemannian geometry. We know what a connection is. Now for metric compatibility, we need a sum of connection. So I have to say, starting from a connection here, what is the connection on the tensor product of gamma? And this can be done via this formula, where you can see at this point we need a braiding. Yeah. So here, since again the order is spoiled, you have to braid omega with nabla, and you can prove that this makes sense, meaning that this gives a right connection on the tensor product. And since we have this sum of connection now, we can say, okay, first what a metric is. This is just a tensor here, so it's a element of the tensor product of forms that is invariant under the braiding, and that gives me a left a module isomorphism here. So this is the non-degeneracy property. And then nabla is metric compatible if it vanishes, so the sum of connection vanishes on G. And okay, so I'm wrapping up. So Yeah, so what we proved is that this is really everything that you need for a Levi-Civita theorem. So meaning that for any triangular Hopf algebra and any braided commutative H-module algebra, you can prove that for every metric, there's one and only one Levi-Civita connection. And this is proven via a braided Kosul formula, which I said. So I was first proving this for H equivariant metrics and connections, and afterwards Paolo was proving it for the non-equivariant case, which is harder. And maybe one more thing to mention is that, so what follows is that on co-triangular Hopf algebras, this means that we automatically get a bicovariant differential calculus, and for any even non-central metric, we have one and only one Levi-Civita connection. I would like to extend this to even more general Hopf algebras, so not using a symmetric braiding. And that's something I'm working on with Paolo, and we are almost there. So we are really close, meaning that we have the crucial tool, which is the sum of connection. This is done, yeah, for the general Hopf algebra setting. This means we have a very natural notion of what metric and metric compatibility is. And we could even prove that there's one and only one Levi-Civita connections for something we call, or I call, quasi-central metrics. So they are really close to being central, but they are multiplied with a function here. Yeah. So for such metrics, we could prove that there's one and only one Levi-Civita connection. And of course, we want to do more. Maybe we can even prove it in the most general case, but that's future work. Yeah. Let me just flash some references. So this was the paper that started this non-central metric business. And those are the two papers of Paolo and mine. And okay, thanks for your attention. Yeah.
Okay, thank you very much. So thanks for the very nice talk. And one question, which is just sort of normal, having Levi-Civita connection or having a connection, you can compute the curvature. This is natural. But then getting some sort of geometric objects like the Ricci tensor or the scalar of curvature, is it possible? And but of course, you know, probably this requires some either additional assumptions or some extra data, or
yeah. Yes. So probably you would need like traces, and of course, in the general Hopf algebra setting, you wouldn't have this. So I mean, for a bicovariant differential calculi, you are in a very nice situation in the sense that you have the fundamental theorem of Hopf modules that tells you that your modules are free modules, and that's very powerful. Yeah? But I'm not sure if this is enough to get traces. So this I don't know.
I mean, in the bicovariant case, I mean, this is very nice because usually in the bicovariant case, I mean, the sort of relation between forms are very nice. I mean, there's antisymmetry sort of. So then you can nicely lift the things to the tensor product. In the tensor product, you can get traces. So probably it will work.
Yeah,
and
so
then it would be nice to see. Yeah.
Would be nice, okay. Yeah. But I was not thinking about this yet.
Thank you very much.
Welcome. Mm-hmm. No. Yeah. So here for this, so this would be my definition in the symmetric monoidal category case. Yeah. So here you don't take all endomorphisms, but you take those ones that satisfy this braided Leibniz rule. Huh? Yes, so this was what's in this proposition here. They are not even a bimodule, they are much, much more. They are a braided symmetric H equivariant A bimodule. Yeah? So you have a lot of structure here. You are getting an H action, you are getting a left and the right A action. And you have this symmetry property that the left A action is just the braided right A action. But yeah, this is a very special case. In the general Hopf algebra setting, it's more difficult. And I think there one would go back to one of your definitions, which I guess is you take the dual. So you start with the differential forms. Yeah, so you can see here, I'm doing it somehow the other way around. So in my case, forms are the dual of vector fields. But of course, you can also say for me, it would be more natural to start with forms and then take vector fields as the dual module. And then you can prove that there's a natural left and right action, just as a dual bimodule, right?
And then when you dualize forms again, you get the same vector field?
No, in general not. And here this is a technical assumption that I tried to hide. So here you would need that vector fields would be finitely generated projective as an A module. Otherwise, you don't get back vector fields as the double dual. You might get something different. Yeah? We can check that. Yeah.
Is there any question from the audience online? Okay, so let's thank again Thomas. And we proceed with the second speaker of this afternoon session. Hello, Joakim. Good afternoon.
Hi, Paolo. You can hear me?
Yes, I do hear you.
Great.
So as soon as the screen is clean for is ready. Okay, perfect. So we can start, and Joakim Arnlind will speak about Levi-Civita connections for a class of non-commutative minimal surfaces.
Thank you very much, and thanks to the organizer for organizing such a hybrid meeting for us who cannot be there in person. I'm sorry about that, but I'm very happy to participate like this as well. So let me start sharing my screen. Like that. Sorry, I have to check. Can you see my screen now?
Yes, we see.
Great. So, yeah, so it's of course related to the topic of the previous talk on Levi-Civita connections, and although a slightly different framework, a slightly different setup, and slightly different applications. So I will be considering Levi-Civita connections for a class of non-commutative minimal surfaces. But in doing that, I'm going to take a detour around modules with Hermitian forms on them and their properties. So what I will present today is based on a paper I wrote in earlier this year, which is now to be published, and then also related to the results in a previous paper together with Jagian Che and Jens Hoppe, which was published in 2016, which is the non-commutative minimal surface part of this talk. I won't say much about non-commutative minimal surfaces because that's another talk, but a little bit since I will apply the results at the end to these surfaces. Okay. So something about non-commutative minimal surfaces. So why did we come to this subject? And well, first of all, the classical theory is a rich subject, still active. And just from a mathematical point of view, you could ask if there's anything interesting in a non-commutative theory of minimal surfaces. I mean, from a physical point of view, it's somehow clear that minimal submanifold equations appear as typical equations of motions. And for instance, in membrane theory and string theory, one finds that operators corresponding to the embedding coordinates have to be harmonic I mean, that's one of the conditions for an embedding to be minimal. So what we did here was to take an equational approach to minimal surfaces. In that, I mean that we're trying to solve non-commutative equations rather than doing things in analog with the classical definitions, which would be that you want to find stationary points of the area integral, a variational approach. So that's how we came to these more equation-like framework. And I want to say more about this now. I will come back to it later, but with the definitions we have of non-commutative minimal surfaces, one can do a lot. One can construct many explicit examples of these surfaces in terms of generators and relations. And one can also prove a non-commutative version of the Weierstrass representation theorem, which tells you how every minimal surface in R3 looks like. And we have a non-commutative version of that, which is in this 2016 paper. So I haven't said anything about what these things are here, and I will come back to that at the end. Now, minimal surfaces is, of course, a metric theory, right? It has to do with the induced metric on the surface when you embed a manifold. And in this 2016 paper on non-commutative minimal surfaces, we did not focus on the metric aspects at all, like connections and curvature. We focused on solving equations related to minimal surfaces. So, and I want to sort of come back to that now, and I want to see, can we compute in a nice way, for instance, connections and curvature of these non-commutative minimal surfaces? And to do this, I will go back to be a little bit more general. And I started thinking about connections on modules with an Hermitian form on them, and what we can say and what kind of statements we have. And so I will start by discussing finitely generated projective modules, which has an invertible Hermitian form. And after that, I will come back and apply these results to these non-commutative minimal surfaces and show you how to compute a Levi-Civita connection to illustrate that in this case, for non-commutative minimal surfaces, they are nice enough so that one can compute these things explicitly. Okay, so let's start with the general things, and these are things you all know. So I start with a non-commutative unital star algebra, and my modules are by default right modules unless otherwise stated. And as we know, for non-commutative star algebras, it's natural to replace the metric with the corresponding Hermitian form instead. Now, just what do I mean here? Well, if I have a star algebra and I have M, it's a right A module, then a Hermitian form of M is a map that takes two elements of M and giving back an element of A. It's the inner product, satisfying these axioms here. So it's you have some kind of symmetry corresponding to the star, that's one. You have a linearity in one of the arguments, in both arguments, and you have a linearity also with the algebra in the second argument that you are all familiar with. And this is what one would replace the metric by on a right module. So now we need to have some assumptions on this Hermitian form. So we want it to be just like in ordinary geometry, we want the metric to be non-degenerate. So we have to formulate that in this language. So to every Hermitian form, you can associate the map, which is called H hat here, going from the module to its dual. And you simply do it by plugging just one of the arguments of your metric. And you see the definition here, H hat on M1 acting on M2 is simply H of M1 comma M2. And this map might be surjective, injective, and so on. And I just call this Hermitian form invertible if this map, H hat, is a bijection. And if it is a bijection, you can define the inverse in this way, which is written here. Okay. And just to illustrate this, what does it mean? for a free module. So we have a free right module, an of rank n, with a basis, e hat I equals 1 to n. And the Hermitian form is determined by some matrix Hij of algebra elements and computed, as you can see here in the formula. And in this case, the Hermitian form is invertible if there exists an inverse to the matrix Hij, which you see here, such that Hij times Hjk is delta Ik times the unit element in the algebra. And of course, here all repeated indices are summed over, which will be in the rest of this talk. So for free modules, it's exactly what we expect. It's just that this matrix defining the Hermitian form is invertible. So just to be able to talk about this a little bit more smoothly, we say that if you take a right module and a Hermitian form and you put it in a pair, you just call it a Hermitian module, as you would do also for C-star algebras and so on. And just to be clear here, let us just define what I mean by homomorphism of Hermitian modules. That's what you would guess. It's just a module homomorphism, and such that it's compatible with H. So if you first compute the H of M1, M2, it's the same thing as mapping them to M prime and then computing H prime of those two elements. And of course, if this happens to be a module isomorphism, we say that phi is an isometry, and we say that they're isometric, and we write that M, H is isometric to M prime, H prime. So that's what I mean when I say that they are isometric. Yes, so now I want to study modules with Hermitian forms that are regular enough to be able to do something, right? So I want the module to be a finitely generated projected module, and I want H to be an invertible Hermitian form. So just to be able to talk about it, we say that we have an invertible Hermitian form on a finitely generated projected module, then the pair M, H is called it a regular Hermitian A module. And those are the things I want to study. Now, so we already noted that if you have a free module, invertibility of the metric, it means that you have really an inverse to the matrix defining the metric. But that's only if the module is free. And you can wonder what happens if the module is not free here. Well, so for regular Hermitian modules, so recall that the module is then projected module, and you can always find an inverse relative to the generators. So if you have EA, A runs from 1 to something, N, are generators of the projected module, and you have H with respect to those generators, you can find an inverse, which is an inverse relative to the generators, and you can write it like this here. Yeah. So that's good enough. It's not a complete inverse, but it's an inverse when you multiply by the generators of the module. So that's fine. And just interestingly, this also characterizes regular Hermitian modules. What do I mean by that? Well, if you have an Hermitian modules and you have a set of generators, and then you have HAB is the components of the Hermitian form with respect to those generators, then M, H is a regular Hermitian module if and only if there exists an inverse relative to the generators as written here in the module. So this property of having this inverse is a characterization of regular Hermitian modules, which is quite useful to have because it allows you to do easier computations in the module. Right. Now, let's see, how do we construct the regular Hermitian modules? Well, this is how you would expect. So for a free module, we have already seen that you can take an invertible matrix H, Ij, with entries in A, and you simply set define the Hermitian form like I've written here. So then, of course, by definition, this is invertible and the module is free, so it's projective, so it's clearly a regular Hermitian module in this language. And as you also guess, if you take an orthogonal projection with respect to H, then you can easily construct regular Hermitian projective modules. And it's simply starting with a free module, an, h tilde, and you assume h tilde to be invertible. And if you then take an orthogonal projection on this module an, then the image of that projection is, first of all, clearly a projective module, of course, and then compared with the metric restricted to the projective module, you get a regular Hermitian module. That metric will also be invertible. So you get a regular Hermitian module. So in this way, you can easily construct examples of regular Hermitian modules that are not free. Now, of course, when you see this, you immediately ask the question which you ask for projective modules, namely, do I get every regular Hermitian module in this way? Certainly, we get every projective module as the projection of a free module, but does it combine together with a metric to give a regular Hermitian module? And the answer is yes. You can construct every regular Hermitian module as a projection of a free regular Hermitian module. And this is how the construction looks like. You start with m, h prime. Now m is a finitely generated projective module. H prime is an invertible metric. And then you define an invertible Hermitian form where you go to the sum of the module, the free module an and its dual an star. Now, just a technical point here, because you say that, well, if an is a right module, then the dual is, of course, canonically a left module. But what's written in the footnote here that I consider this left module as a right module via the star on the algebra, which you can always do. You can define the right action as the left action with a star or the other way around. So it's considered as a right module here. Now, on this module, you can define this metric, what's written here, B, the Hermitian form, and it will be invertible. And you can construct a projection on this free module, which is orthogonal with respect to B, and such that the image of this projection is isomorphic as a Hermitian module to the original module you started with. Sort of showing that every Hermitian, regular Hermitian module can be obtained in this way, which is, of course, also useful for doing computations. Okay, so so far, modules and metrics or Hermitian forms on these modules. Now, we want to come to projections. And I want to do it this in a way which is closely related to derivation-based differential calculus. So in derivation-based differential calculus, you have a set of derivations on which you base your calculus. So just to have something to talk about, I just call it a Lie pair, an algebra A together with a Lie algebra of derivations, G. And we assume this A, again, to be unital star algebra. And this Lie algebra to be a star-closed Lie algebra of derivation. So you take the star of a derivation, it should still be in the Lie algebra. And that's our basic data that goes into defining connections. Now, this is, of course, a standard definition. Now, if you have such a pair, you have algebra and you have derivations, you can define, and you have a module, you can define a connection on this module with respect to the algebra and the derivations. And this is a map taking a derivation, a module element, and giving back a module element, such that the usual axioms hold. It's linear in both arguments of a C, and importantly, number 3 here, you have Leibniz rule for the connection when you take the connection of M times an algebra element. So that's all standard. Okay. Now, this is perhaps also standard, that if you have such a Lie pair and you have a right Hermitian A module, now, so we have an algebra A, we have a Lie algebra of derivations G, we have a finitely generated projective module M, and an invertible metric H. Then we call the connection Hermitian or compatible with the metric if the following relation holds, which is, of course, looks very familiar. It's just the ordinary compatibility with a connection with the metric. And we have to plug in a star here of D star because one of the arguments of H has an extra star on it. Now, let's connect it a little bit to the construction of this regular Hermitian modules, namely that if you have a connection on a free module, a free regular Hermitian module, and you take an orthogonal projection again, then P composed with the connection is again a Hermitian connection on the image of the projection. So that's one easy way to construct Hermitian connections on a projective module. So, and for free modules, you can easily derive explicit expressions for all the Hermitian connections, which looks very much like in differential geometry. So if you have a Lie pair and you have a basis of G, which is denoted by dA here, and you have E hat I, which is a basis of the free module, then you get a Hermitian connection by the formula 1, and for arbitrary gamma, which satisfy a Hermitian condition, which you find here. Yeah. So for all the gammas here, you have an Hermitian connection. So that's quite easy. Now, just combining these with the previous results we had, we can conclude that there exists a Hermitian connection on every regular Hermitian A module, simply because of the fact that every regular Hermitian module comes from the projection of a free Hermitian module. We can construct Hermitian connections on the free module, and finally, we know that the projection of such a connection is a connection, Hermitian connection on the projective module. So these modules are sort of well suited for studying Hermitian connections, since we know that they always exist on these modules. There exist many, but at least they exist. Okay. Now let me now come closer to what I want to apply this theory to. So I want to add some more data. I want to take the Lie pair AG, and I want to add some elements of the algebra x1 to xn, which you should think of as embedding coordinates of this manifold somehow. And lack of a better name for it, I just called it here embedded non-commutative manifold, consisting of the data algebra A, the algebra of derivation G, and a number of Hermitian elements, which you can think of as the embedding coordinates. And I do this because I want to come closer to the non-commutative minimal surfaces. Now, in this case, you can define a map from the Lie algebra of derivations into a free module by using the x's, as in definition 2 here. Right? So you map derivation into the free module by simply differentiating each component of the vector in the free module. And now I do this, and I generate a module by all these, the image of phi, that's the module I will call T sigma. That's the module generated by the image of phi. And that's what I will refer to as the modular vector fields of this triple or embedded non-commutative manifold, if you want. So phi is a map from derivations into the module, the free module in this case, and the image is called T sigma. Now, just a technical note here that since G is star closed, we can always find a basis of Hermitian derivations. And it's clear that the image of these Hermitian derivations by phi generate the module T sigma, so we can use them as generators, and we should write EA for the image of these Hermitian basis of the Lie algebra, and they generate the module. And we will also use this definition or notation for the second derivative of these elements xi. So what is this phi? Well, if you compare to differential geometry, phi is sort of the derivative of the embedding coordinates, the vector consisting of the derivatives of the embedding coordinates, and that's a tangent vector, right, at each point. So the image of phi spans the tangent space at each point. And now we're talking more globally, so the image of phi sort of generates the vector fields of your embedded manifolds. That's how we should think about it. Now, when we have this in place, we can talk about torsion freeness in a slightly different way than we saw in the previous talk. But first of all, we let H0 be the metric here, which is defined by the identity matrix if you want. We call H the restriction of this metric to the submodule T sigma. And in the following, we shall assume that T sigma is a regular Hermitian module, and that we can apply the results we have in the previous section. This will clearly be true for the non-commutative minimal surfaces. Now, and once we have this phi, we can talk about torsion freeness. Namely, you think of phi as mapping the vector field into the derivation into the vector fields. Now, in ordinary geometry, we know that phi is just the correspondence, the one-to-one correspondence between vector fields and derivations. But in this context, phi is something more, can be something more general. And in previous papers, we also considered general phi. Here we have a specific phi, but you can also consider general phi. So this is the way then to write down torsion freeness in terms of a map phi, which you could call an anchor map, mapping derivations into sections of your vector bundles or vector fields. And if you have a connection, a Hermitian connection, which is torsion free in this way, I will call it a Levi-Civita connection. So yeah, that's my Levi-Civita. Yeah?
Sorry. It's 25 minutes you're speaking. Every speaker is given 30 minutes. So you are entering question time, the question section.
Okay, I see. Okay.
Appropriately.
Then I will just right. I thought it was the 30 minutes. So okay, thanks. So what you can do with this then, I will just stop here, is that you can explicitly at the end, let me just show you the last slide here. Now, for non-commutative minimal surfaces, you can compute Levi-Civita connection in this way, and you get rather explicit formulas. You could always also call them simple formulas for the Levi-Civita connections. Now, phi and phi bar are generated by T sigma, are generators of T sigma. And so these are the connection acting on the generators of the module. This will be a free module in this case. So showing somehow that, well, if you do this in general, you get very complicated formulas. But if you do it for the non-commutative minimal surfaces, they have a nice structure so that you can actually compute it and it becomes manageable. Okay, sorry, Paolo, I will stop there. Thank you very much. Yeah.
Well, thank you to you.
Yeah.
Now it's question time. Other questions from the audience? Other questions from the online? Okay, so Joakim, given that there was no questions, if you want to add a comment concerning this last part that you were very fast, please go ahead.
Yes, yeah. But maybe I can just say now what is that? Maybe I can just say to you, what is that a non-commutative minimal surface? Maybe I can just say that to give you something to take away here, just for 2 minutes. Yeah.
Yes.
Yeah. So maybe that. So now just let me set some notation first. You all know the Weil algebra, unital algebra generated by elements u and v, satisfying that the commutator of u and v is IH bar 1. Now that algebra satisfies the Oeber condition, which implies that it can be embedded in a field of fractions. Okay, and that can even be made into a star algebra in a standard way. Now I let G2 denote the Lie algebra generated by two inner derivations, d hat u and d hat v, as written here. They're just inner derivations when you commute with u and you commute with v, and you divide by IH bar for consistency here. Now, what do I mean by a non-commutable minimal surface? Well, I mean this fraction field of the Weil algebra, this Lie algebra of the commuting two derivations, and a set of embedding coordinates, just like we saw before, satisfying certain things, right? The most important thing is this equation here. Now, this equation is a double commutator equation. Now, it's an analog of the sum of second derivations, which is an analog of the Laplace operator on the embedded manifold. You can make this much more precise with relation with Poisson brackets, Poisson algebras, and the Laplace operator. But I just want to tell you that the important equation that these elements solve is that they solve that this double commutator equation is equal to 0 for each xi here. And it looks not so easy to construct solutions here, but we can write down a framework which provides you with infinite number of solutions to this equation here. And that was the original motivation for introducing non-commutative minimal surfaces in an equation-like way here, simply demanding that the embedding coordinates are harmonic with respect to the induced metric on the surface. That was 2 minutes. Thank you.
Thank you. And one very quick answer to a very quick question, if there's one more. And so I did understand it correctly, existence of connections, but is there also uniqueness for this in this setting?
No, actually you get with these loose axioms, you get a whole family of Levi-Civita connections satisfying the Hermitian. So you could imagine putting more constraints on the connection, perhaps some reality constraints or compatibility with the star in the algebra. But if you just write it down like I did, there is a whole family of Levi-Civita connections on this algebra. So not equal to what I did in previous papers where I could show the uniqueness of Levi-Civita connection, but that is due to a lot more assumptions, reality assumptions on the metric and on these objects. Yeah.
Thank you.
Thank you very much.
Joakim? And we pass to the third speaker of the afternoon, that is also online, Gerardo Morsella. The last talk will be in presence by Ciao, Gerardo.
Hello, thank you.
Yes.
I will share the screen.
No, the last online talk, sorry. The last online talk. Ciao, Gerardo. So it's 25 minutes talk plus 5 minutes questions.
Okay. Thanks a lot. Can you see my?
Yes. Please tell us about UV and IR finiteness on quantum spacetime through perturbative algebraic QFT.
So thanks a lot for the introduction and of course for inviting me to this nice meeting. I would have loved to be in Corfu in presence, but unfortunately it was not possible because of teaching duties. But okay, so I'm glad anyway to be able to give this talk online. So the talk is based on these two papers, which are here, one on CMP and the other one on mathematical physics, analysis, and geometry, which have been done in collaboration with Sergio Dobliger and Nicola Pinamonti. Sergio Dobliger in Rome and Nicola Pinamonti in Genoa. Oh, it seems that my slides are freezed. Oops. Sorry. Let me see what happens. Okay, now it seems to work. Okay, so that's the outline of the talk. I will first recall some facts about Dobliger-Federer-Roberts quantum spacetime and quantum field theory on it, and then I will discuss how perturbative algebraic quantum field theory, which is an approach to perturbative quantum field theory, which has been developed in the last 20 years, can be adapted to treat quantum field theory on quantum spacetime, on Dobliger-Federer-Roberts quantum spacetime. And then, if time allows, I will discuss briefly a cosmological application of this analysis, and then there will be the conclusions. So I guess many in this audience know this old argument by Dobliger-Federer-Roberts in 1995. They observed that combining quantum mechanics and general, sorry, that's a mistake. It should be GR, general relativity. If you want to localize a quantum state in a small region, then because of general relativity, because of quantum mechanics, you have to give a lot of energy to the system, and general relativity tells you that this will create a trapeze surface around your localization region. So in order for this localization experiment to have an operational meaning, you want to require that this trapeze surface does not form. And this leads you to some uncertainty relations between the coordinates q mu of the event that you want to observe. And these uncertainty relations, of course, involve the Planck length. And these uncertainty relations can be implemented by sister algebra in the same sense that Heisenberg uncertainty relations are implemented by the canonical commutation relations. So they formulated this sister algebra of quantum spacetime E, which is, as a sister algebra, is isomorphic to a trivial field of compact operators over a certain manifold sigma. And this sister algebra comes equipped with an automorphic action of the Poincare group. So in this sense, from this point of view, this quantum spacetime is Poincare covariant. Then they went on to define free scalar fields on quantum spacetime by using the usual Weil-Wigner-Moyal quantization. So here phi check is the anti-Fourier transform of the usual free scalar field on commutative spacetime. You take the tensor product with the exponential e to the a k cube, where q are the generators, the operators which generate the sister algebra of quantum spacetime, and you integrate, and you get an element which is formally an element of the tensor product of the usual free field algebra times the algebra of quantum spacetime. This free field is non-local at small distances, but locality is recovered as lambda Planck goes to 0. So this means it's non-local as distance is small with respect to lambda Planck, but the local commutations relations are recovered when the distances are large with respect to lambda Planck. Then one, of course, wants to go on to discuss interacting fields on quantum spacetime, at least perturbatively. This can be done in several ways, which unfortunately are non-equivalent on quantum spacetime, even if they are equivalent on non-commutative spacetime. So there are different possibilities of introducing interactions, and one has to choose one of them. In this talk, I will focus on the so-called Hamiltonian approach and quantum big product. So this means that the interaction is introduced by an interaction Hamiltonian, which is defined by this formula here, where this integral, this three-dimensional integral is a notation for a certain conditional expectation on the sister algebra quantum spacetime, which generalizes the spatial integral in commutative spacetime. G is a coupling constant, and this phi q to the n double dot q is the so-called quantum big product, which is a non-commutative generalization of the limit of coinciding points of a product of fields at independent coordinates, where this limit it has to be taken in a way which is compatible with the commutations relation. So I don't want to go too much into the details, but anyway, it is possible to define this quantum big product in a way which generalizes the ordinary coinciding point limit. And this defines the interaction Hamiltonian. And then one defines the S matrix by the usual Dyson series, and one finds that this S matrix is actually equivalent to the S matrix of a non-local quantum field theory on commutative Minkowski spacetime, ordinary commutative Minkowski spacetime, and with the interaction Hamiltonian, which is given by this rather long formula, where the important point is that there is this non-locality. The non-locality is implemented by this Gaussian kernel here, where x here is the point which has time coordinate t and space-like coordinates both x. And they showed in this paper, together with, so this was Barnes, Doppler, Federnager, and Piacitelli, they showed that this S matrix, which is obtained this way, is term by term unitary and it's free of ultraviolet divergences, where one has to replace the coupling constant G by a certain compactly supported function, which implements an infrared cutoff. So putting an infrared cutoff, the theory is ultraviolet finite, at least perturbatively. But then, of course, one wants to remove this ultraviolet cutoff and to send this function to a constant, for instance, to 1. And this proved to be difficult to control, even if Alexei Bykov, in his PhD thesis, which was done here in Tor Vergata last year, showed that this adiabatic limit is possible, at least for the green functions of the theory, not directly for the S matrix elements, which is the so-called strong adiabatic limit, but at least for the green functions, it is possible to perform this limit, which is the so-called weak adiabatic limit. So the goal of this talk is to find a way to discuss this adiabatic limit. using this machinery of perturbative algebraic quantum field theory. So as I said, perturbative algebraic quantum field theory was developed by a lot of people, Brunetti, Deutsch, Fredenhagen, Reisner, Hollands, a lot of people, in order to construct perturbatively algebras of observables in quantum field theory. And the main goal of this talk, of this work, is to try to adapt perturbative algebraic quantum field theory to quantum spacetime and to study the perturbative expansion and the limit in which the infrared cutoff goes to 1. So what's the starting point? The starting point is that the free scalar field algebra is isomorphic to an algebra F, which is made, whose objects are certain functionals F on field configuration, so functions on ordinary Minkowski spacetime, where suitable means that there are some restrictions on the wavefront sets of the functional derivatives of this functional. And these restrictions are made in such a way that it is possible to define this star product between two such functional by this formula. So one takes little m here is the usual pointwise product, and then one deforms this usual pointwise product by the exponential of this functional derivative operator, where delta plus here is the usual free field 2-point function. So this star product is a deformation of the ordinary product in the direction, in a sense, of the free field 2-point function. Then one can define the free vacuum state, which is just the evaluation of each functional at 0. And together with this star product, which is non-commutative, one has to also introduce the time-ordered product of two local functional by an analogous formula, where instead of the free field 2-point function, one puts the Feynman propagator. This definition of the time-ordered product at first only makes sense for functions f and g which are local and that disjoint supports, where local means that their functional derivatives are supported on the diagonal, so they are distributions in n variables whose support is where all the variables coincide. And so with this formula makes sense for this kind of functionals, and then one has to extend this formula to this time-ordered product to all local functionals, maintaining the property of causal factorization, which is simply the fact that this time-ordered product is the time-ordered product corresponding to this star product. So when the support of F is in the past of the support of G, then the time-ordered product and coincides with the star product in the reverse order, and when the support of F is in the future of the support of G, the time-ordered product coincides with the star product in this order. And this procedure of extension of this time-ordered product to all local functionals is the procedure of renormalization. So this can be done. This extension can be done. There are some ambiguities in this extension, and these ambiguities are classified by a renormalization condition. This was the subject of this old paper by Epstein and Glaser. When one has defined this time-ordered product, one can define the S-matrix, of course, as simply as the time-ordered exponential of some interaction Vg. And this S-matrix satisfies this important property, which is also called causal factorization, because it is a consequence of the causal factorization of the time-ordered product, which says that if you take three functional f, g, and h, such that the support of f does not intersect the past of the support of h, here j minus is the causal past of the support of h, then this s of f plus g plus h factorizes in this product of s of f plus g star s of g star s of g plus h. So our idea was to try to use this machinery to treat the non-local theory, which on commutative spacetime, which is equivalent to quantum field theory on quantum spacetime. But the first problem that one encounters if I want to do that is that if one takes as VG the effective non-local interaction for quantum field theories on quantum spacetime, so the one that I wrote before, this one, this interaction here, then one gets that the S matrix defined by this formula is non-unitary, because it's just the S matrix which is obtained by using the so-called field rules, and one knows that such an S matrix is non-unitary. So this is of course unpleasant. So one would like to do better. And the key observation in order to do better is that in the limit in which the cutoff function the infrared cutoff goes to a constant, the non-local interaction which I had in the previous slide is equivalent to this other non-local interaction, in which the non-locality is attached to all the fields, to the single fields. So one has this Gaussian non-locality, and one takes the convolution of the field with this Gaussian kernel, and then takes the nth power. And so one can use this interaction instead of the other one, and this is much better. Why it is much better? Because if you define so this iota lambda is just the convolution of the field with the Gaussian which I had in the previous slide. So this G lambda is just this function here with its normalization. And one can pull back the action of this iota lambda to the functionals which define the free field algebra. And if one does that, one finds that this non-local interaction is the image under this pullback R lambda of a local interaction. So this functional here as a functional of phi is a local functional. And when one has a local interaction, then the S matrix is automatically unitary. So this suggests that instead of using this interaction and the ordinary star product, the star product which I had before, one can use this other interaction and deform again the star product by using this R lambda. So this R lambda maps the star product to a new star lambda product, which is a further deformation of the product on F, which is given by a formula which is analogous to the one which we had before, but now the direction of the deformation is this delta plus lambda, which is obtained by convoluting on the left and on the right the two-way function with this Gaussian kernel. So one gets another algebra, which is again, which is the same algebra as before as a set, but with a new star product, this star lambda product. And in this other algebra, one can use a local interaction instead of a non-local one. Of course, one has to define a time-ordered product with respect to this new star lambda product, and this is done by the same recipe, where now one has a deformed delta F lambda Feynman propagator given by the usual formula. And the nice fact is that this delta F lambda is a continuous bounded function, and this implies automatically that this T lambda product is directly defined on a suitable subalgebra A of the algebra F, which is the algebra which is generated by the fields, but not by their derivatives, without any need of renormalization. So while the usual T product, the product has to be defined by renormalization, here it is automatically well defined without needing to renormalize anything. And so one can use this local interaction to define an S matrix using this deformed time-ordered product, and one finds that this S matrix is ordered by order finite, as I said, so there is no renormalization needed. It's unitary in this star algebra A star lambda, so it's unitary with respect to the star lambda product. And it enjoys, so before in the usual commutative spacetime, the S matrix enjoys this causal factorization property. Now, causal factorization does not hold anymore, but there holds a remnant, which we call a temporal factorization property, which tells you that the same factorization holds when the support of the first functional A is later than the support of the last functional C in the Lorentz frame fixed by star lambda, because I should have remarked it before. This star lambda is not Lorentz invariant. It fixes a Lorentz frame simply because here in G lambda this bar denotes the Euclidean norm. So this is not Lorentz invariant. It's the Euclidean distance, not Lorentz distance. But anyway, in the frame fixed by this Euclidean distance, one has this again this factorization, which is important because one can use it to perform the adiabatic limit, so to remove the infrared cutoff. The first step is to define interacting fields by the so-called Bogoliubov map. So given a functional A, the corresponding interacting observable is defined by this formula. S matrix star, this should be a star lambda, sorry, no, not a star. This is a star lambda, A time ordered lambda product S matrix. And this temporal factorization property implies that this interacting observable only depends on the restriction of the infrared cutoff function to the past of the support of A. So if you modify the infrared cutoff in the future of the support of A, this observable remains untouched and invariant. And so this can be used in the following way. So first one can define the free and interacting time evolution. So the free time evolution is simply take the configuration field phi and translate it in time, while the interacting time evolution is intertwined with the free time evolution by this Bogoliubov map RV. And these two time evolutions are intertwined by a cocycle UT, which is defined by this formula, which is, so it is essentially the analog of exponential of the interacting Hamiltonian times exponential of minus the free Hamiltonian. It's essentially the same object.
So 2 more minutes or before the 5 minutes for time for questions.
So I will try to. So so the idea is, since, as I said, the interacting observables are independent of the cutoff in the future of the support of A, one can take the infrared cutoff as a product of a function of time and a function of space, and the function of time is one in the future of a certain time, and the support is also in the future of this time. So this means we think of the interaction as switched on at a certain time, which I denote by minus epsilon. And then the interacting vacuum should be obtained when this switching is translated back to minus infinity, which is the same as translating in the future the support of all the observables. So and then taking the spatial cutoff AH to 1. So the interacting vacuum should be obtained by this formula. There are some problems in controlling these limits, and okay, I will not go too much into details. These problems can be circumvented by approximating the vacuum by interacting KMS states, so states which are equilibrium states at a certain positive temperature. When the temperature goes to 0, these states are supposed to approximate the vacuum, and so one can go around, instead of doing the limit directly, this limit T to infinity directly on the vacuum, then one takes first the limit on t going to infinity on the equilibrium states, and then one takes the temperature to 0. And in the end, one gets this result. That so here omega beta lambda h is the interacting equilibrium state with a fixed spatial cutoff h, and one can show that this limit in which one takes together the spatial cutoff to a constant and the beta to infinity, so the temperature to 0, exists and defines a state which is invariant under space-time translations, and therefore this can be interpreted as a vacuum state, as the interacting vacuum state of the theory. So in this way, one removes the infrared cutoff. Okay, just a quick word about the cosmological application. So in another paper together with Sergio Dobrica and Nicola Piedamonti, we tried to generalize the original Dobrica-Federer-Roberts argument to a curved space-time, and what we obtain is that, for instance, in a cosmological space-time, there is an effective Planck length which diverges near singularity. So near the Big Bang, one should take lambda Planck going to infinity, and then if one consider this limit lambda Planck going to infinity, one finds that the theory reduces to a free theory. So the interaction disappears, and the star product reduces to the ordinary product. Interacting observables reduce to the free observables, and the interacting vacuum reduces to the free vacuum. So this suggests that near the Big Bang, interactions should disappear, and moreover, correlation length of free fields should diverge, because the correlation length is proportional to lambda Planck. The non-locality is proportional to lambda Planck. So this suggests that there seems that no degrees of freedom remain at the Big Bang, and so this could provide an alternative solution to the initial conditions problem. So if there are no degrees of freedom, there is no initial conditions problem. And okay, so that's the summary of the talk. And as an outlook, one could try, for instance, it would be interesting to try to do this for more physically interesting theories like for instance QFT on quantum space-time, among other things. Okay, I'll stop here. Thank you very much for your attention.
Thank you. So are there questions, comments? Yes, there is a question from Harald Steinhacke.
Hi. So I was wondering, so if I understood you correctly, then the basic point of your construction was to define the interacting Hamiltonian in a particular way using this exponentially damped version of an interaction.
That's not a definition. That's a consequence of, so the original definition is this quantum weak product on quantum space-time, and then if you compute, so the original definition of the interaction is by this quantum weak product, which means you take n copies of quantum space-time, and you compute on differences of the Q's. You evaluate states of optimal localization on differences of the Q, and this generalizes this limit of coinciding points. That's the definition of the interaction Hamiltonian. Then you find that this is equivalent of considering non-local interaction on ordinary space-time, on computed.
I mean, what I'm trying to get at is, so if I would, so I have a feeling that you couldn't probably do this in the context of gauge theory, and some of the reasons for me at least is the following: that if you want to define an action which is gauge invariant, then you somehow you have basically very little freedom to adjust such things because you want to preserve the cyclic properties. And as far as I know,
I can hear very well. Could you please? So
whenever you have
noisy, so I cannot hear you very well.
Okay, yeah. And because then you would unavoidably recover in any operator algebra these highly non-local states which Joakim mentioned this afternoon, and then you are back to the usual ultraviolet infrared mixing probably.
Sorry, could you repeat more slowly? It's very fuzzy, the sound.
Okay, sorry.
I'm sorry.
Okay. So my sort of problem with this kind of construction is usually that if I try to generalize it to gauge theories, in gauge theories one has to preserve the cyclic properties, so one needs to have the associative star products and whenever if they are realized based on some kind of operator algebra, you always have highly non-local states like the string states which were discussed by Joakim this afternoon, and highly non-local interaction which you cannot suppress, and then you get ultraviolet infrared mixing effects which are the usual disaster. Which somehow in this construction you manage to avoid this. I don't completely understand how, but it seems to be in this interacting Hamiltonian. So what about gauge theory? Basically, that's the question.
Yes, so I cannot say too much about gauge theories because we didn't yet try it. So my impression is that this ultraviolet infrared mixing is also present in scalar field theories, even if in a milder form, and through this approach, this is completely avoided. So there are some formulations of, for instance, QED on this quantum space, of this Doppler-Federer-Roberts quantum space-time, which could be, I think, it could be worth to understand if this machinery can also be applied to them. So, but unfortunately, at the moment, I cannot tell you much more than this.
So thank you for your talk. Let's take it. Let's see whether there is some questions from the online audience. No question from online audience. So we thank you again, Gerardo.
Thank you.
And we pass to the last speaker, who is Daniele Oriti, who is here in presence. Daniele will speak about quantum gravity states as tensor networks, entanglement, and holography. Entanglement and holography in spin networks. Please.
Okay, good. So first of all, thanks to the organizers for the opportunity to give this talk. So I'm going to discuss entanglement properties of quantum gravity states. And I give you first a little bit of motivation, just a couple of slides to clarify where I'm coming from. So I would argue that recently there's been a change in the dominant perspective on quantum gravity, on the quantum gravity problem, from the traditional view, the straightforward one, of quantum gravity as the result of quantizing classical generativity or some other classical theory of gravity, a modification of GR, to the idea that quantum gravity should be some more abstract quantum theory of some sort of space-time constituents to be understood, with space-time, geometry, fields, and gravity as emergent concepts. Now, this is motivated by a number of results in semi-classical physics and beyond, and it is also motivated by several results in actual quantum gravity approaches, which suggest this type of fundamental entities that are not directly quantized fields, or find further limitations to the usual space-time and geometry intuition. And of course, this type of scenario raises a number of questions. The first one is, what type of entities are these constituents? And in general, it brings forward the view of space-time as some sort of background independence or peculiar quantum many-body system. Then, of course, we have concrete models from a number of different quantum gravity approaches. I work in particular on the tensorial group field theory formalism, in which the proposed atoms of space, the constituents, can be understood as quantized tetrahedra. But this is just one particular context. With the idea of space-time and geometry as emergent comes often, and recently in a rather forceful manner, the idea of space-time geometry coming out of the entanglement properties of the fundamental constituents. And in particular, there are many supporting results for this conjecture, for this conjectured correspondence between entanglement and geometry. And most of them come in the ADS-CFT context. And I mention here just a few that would be relevant for the following. So as I said, this concrete realization of the idea are mostly in the ADS-CFT context, in which, in fact, you have a notion of field theory, at least at the boundary of the CFT, and the geometry that emerges is the bulk one. So it's only part of the complete story that we are after. I point out at this stage that the idea that geometry should come out of entanglement is in fact a necessity, a logical necessity in any quantum gravity approach in which space-time is emergent. Because you're going to have quantum building blocks and you have to reconstruct geometry, and geometry will have to be reconstructed from the interaction and therefore the entanglement, the correlations between the fundamental building blocks. This motivates me and colleagues to look for a realization of this idea in a full quantum gravity context, like the type of formalisms we work on, in which there are no space-time or fields to start with. So the context in which I'm going to present some results today is that of spin network states. So if I give you a graph, a set of nodes with links connecting them, then I can define a Hilbert space associated to that, which is an L2 space over copies of the group associated to the links. And you have an invariance under the group action at the nodes. This is the typical Hilbert space of a lattice gauge theory, by the way, with a gauge group G. If you expand any state, any wave function on this Hilbert space in irreducible representations of the group, you will realize that you have a complete basis given by labeled by graphs with links with associated irreducible representations and intertwiners of the group invariant tensors associated to the nodes. Well, such element of the basis is indeed a spin network function. And a spin network is therefore such a state defined by a graph, an assignment of irreducible representations, and an assignment of intertwining labels. Now, spin network states arise, in fact, in several related quantum gravity approaches, First of all, in canonical loop quantum gravity, where you have a full Hilbert space, at least at the kinematical level, given by the union of the Hilbert spaces defined here for all possible graphs, at least traditionally embedded in a manifold, but there are more abstract versions. And then in order to construct a Hilbert space out of this union, you impose some appropriate equivalence relation. In the spin foam context, that can be seen as a covariant version of loop quantum gravity or simply as a formulation of lattice gravity in group theoretic language, you often consider the full Hilbert space to be just the direct sum of Hilbert spaces associated to graphs. In the group field theory context that I mentioned, then where you have a field theory for simplicial building blocks, where you have a Fock space of spin networks, the building blocks being in fact associated to single vertices of a spin network graph, which you glue together as an interaction process. In all this formalism, you also superpose over the combinatorial structure, over the graphs. Now, there is a discrete geometric interpretation for spin network states. First of all is the topological correspondence I mentioned. For a given spin network vertex with an intertwiner label at the node, 4 outgoing links labeled by 4 irreducible representations, normally of SU2. Then you have a dual representation in terms of a single tetrahedron, and the gluing is just the identification and tracing over the shared angular momentum indices. And then you have areas for the triangles, which are whose spectrum is labeled by the spins, and volumes for the cells, for the simplices, whose spectrum is labeled by the intertwining labels, which are further functions of the spins. So since it's the last talk, I already give you my conclusions in case you are too tired to follow all of the rest, but this is also a summary of what I'm going to talk about in the following. I'm going to show you in what sense these spin network states can be understood as generalized tensor networks, which are tools used extensively to capture entanglement properties of quantum many-body systems, and they're extensively used also in the context of ADS CFT for all those relations between entanglement and geometry that I mentioned. I will show you that thanks to this correspondence, you can also see directly a primitive link between entanglement and geometry at the level of discrete geometry in spin network states. And then I will tell you about recent results about the definition of boundary maps and holographic conditions for such maps associated to quantum gravity states, and the reconstruction of a Ruta Kanayagi formula for spin networks, including bulk corrections to the formula. And then I will show you some tentative connection to black holes. Okay, first about the correspondence between quantum gravity states, spin networks, and tensor networks. This is in fact quite immediate if you know what is the definition of a tensor network, and in particular, the definition of so-called PEPs, projected entangled pair states, which is a class of tensor networks. These are just tensors associated to nodes, and then link states, which correspond to maximally entangled pairs contracting the tensors along the links of a network formed by these states. So in fact, the moment you, so this is the definition of a PEPs tensor network. The moment you have invariant tensors, you talk about symmetric tensor networks. And if you have the tensor assignment governed by some probability distribution, then you talk about random tensor networks. And as I anticipated, as I already mentioned, tensor network techniques are crucial in the context of the ADS-CFT correspondence for holographic bulk reconstruction, for the entanglement geometry results, and so on. Well, now the spin network states that I introduced from the quantum gravity point of view have a very similar structure, in fact. You can immediately realize that they can be, the graphs associated to the spin networks are defined just like tensor networks by taking invariant tensors at the nodes and gluing them by a link map, just like in tensor networks. And this is in fact imposing a maximal entanglement between the degrees of freedom along two semi-links. This means that a generic spin network in which the fundamental tensor is in fact a group intertwiner is just a symmetric tensor network. It also means that because in quantum gravity we have linear superpositions of spin networks on a given graph, we automatically deal with linear combinations of PEPs. And it also means that the fully general quantum gravity states in which you also superpose over combinatorial structures, over graphs, they're really fully generalized tensor networks. And they can be given also a second quantized reformulation in the group field theory, tensorial group field theory language. And all these theories, all these quantum gravity formulas will also assign a dynamics for the creation annihilation of such generalized tensor networks. Now, recall the hypothesis of an entanglement geometry correspondence. Well, this correspondence has a primitive, discrete version in the context of spin networks. Indeed, as I've just mentioned, the graph, the network associated to the quantum gravity states is just an entanglement pattern, as I emphasized. And if you also recall the fact that we have an associated notion of surface area for each link and volume for each node, you realize that not only we have an entanglement connectivity correspondence like the one suggested by Van Ramsdonk and others in the context of ADS-CFT, but we also have a primitive entanglement area correspondence between, in fact, the area spectrum for the surface dual to a link goes with the entanglement measure along the same link. And the volume associated to each node is proportional, in fact, to the entanglement measure between the degrees of freedom that are incident associated to a node. The next point is to start studying quantum gravity states and on the one hand realize that also thanks to this correspondence with tensor networks, you can use them to define maps between bulk and boundary data for a simplicial complex, and that you can realize a discrete version that fully quantum geometric of the Ruta Kanayagi formula. So we consider a generic spin network state, as I've introduced earlier. So there is a graph, there are spin labels associated to the links, there are angular momentum projections, but these are all contracted following the pattern of the graph. And then there are intertwiner labels associated to the nodes. In what follows, I will in particular consider special cases in which the wave function is factorized per node, per vertex. For a graph with open links, we can identify boundary degrees of freedom, which are the spins and the angular momentum projection numbers associated to the open links, the spins associated to the bulk links, and the intertwining labels associated to the nodes, and the last two sets of data form the bulk, what I call the bulk degrees of freedom. In general, these are not decoupled. They will decouple if the spins on the bulk are all fixed. In that case, you can in fact decouple bulk and boundary data, and this can be will be crucially used in what follows. Given a generic state with this identified boundary and bulk degrees of freedom, you can define a map from the Hilbert space of bulk degrees of freedom to a Hilbert space of boundary degrees of freedom, whose kernel is in fact just the spin network state you started from. So this is just a reinterpretation, a rewriting of the same state as a map from a boundary state to a bulk one, or vice versa. Now, this is in the fixed spin case. In the general case, you have to embed your state into a broader, into a larger Hilbert space, but the definition proceeds in exactly the same way. So the point here is simply that any given quantum gravity state of this spin network type can be understood as defining a map from a set of boundary degrees of freedom to a set of bulk degrees of freedom, or vice versa. Now we ask, what is the condition for the so defined map to be isometric? Why we find it interesting is that we consider this as a necessary condition for considering the same map as holographic. If there is a duality between a tier on the bulk and a tier on the boundary, then the scalar products should match for observables. Of course, holography is a much richer and broader concept, but we focus just on one aspect of it, which is this isometry. Again, we first ask what is the isometry condition for such map in the fixed spin case, and we translate that into the property of the reduced bulk density matrix to be maximally mixed, so to have maximal entropy. So you're going to have isometry if the reduced density matrix associated to the bulk is maximally entropic. As an entropy measure, we use the second Renyi entropy. We write it down explicitly, and then we take two crucial approximations, two further steps. One, we consider the vertex wave functions, the quantum state associated to a vertex, to be randomized with some uniform probability measure. This is the simplest choice you can take. You can there is some word generalizing this. Second, we go in a large spin approximation. So we increase the number of degrees of freedom associated to our states, because the number of degrees of freedom for each Hilbert space associated to a link is twice the value of the spin plus one. In this approximation, then the average Renyi entropy can be approximated by minus the log of the ratio of the average of these two quantities. Now the whole point is to compute under which conditions, for which states, the entropy is maximized. The calculation is done efficiently by mapping this problem into the minimization of the energy of an associated Ising model. How much time do I have to know if I have
exactly fine?
Okay. So I don't tell you exactly how the map works. Take my word for it. The calculation of the Renyi entropy becomes the minimization of the energy associated to an Ising model defined on the same graph on which you have your quantum gravity data. And what we find is that If you have fixed the spins, then in the homogeneous case, when all the spins are equal, all the bulk spins are equal, the map can just never be isometric. In the inhomogeneous case, when you have different spins, they are fixed, but they are different in different links, then we find an isometric condition, and the main idea is that the more inhomogeneous it is, the more your map approaches isometry and your entropy is maximized. And then we also generalize the same procedure and the same calculation to the case in which you have superpositions over spins. You sum over spins. So not only you assign them in all possible ways, but you sum over possible assignments. The calculation is much more involved. You have to adapt a number of steps, but you can do it. You obtain a well-defined, precisely defined condition for isometry. And the point is that now the dependence on the combinatorics of the graph becomes even more relevant. If the number of boundary edges is of the same order as the number of bulk vertices, then you can have an isometry realized for rather general configurations of the spins. So rather general class of states. If instead the number of boundary links, the open links, is much smaller than the number of vertices in the bulk, then you have a chance of having isometry only for very, very large boundary spins. Now, last 3 minutes or 4 minutes to show you how, with the same setup, in the same context, you can derive a Ruta Kanayagi formula. Now, same class of states, open links, boundary data, bulk degrees of freedom, both spins and intertwiners. Now you consider a different type of entanglement, that is the entanglement between the degrees of freedom on a portion of the boundary and the rest of the degrees of freedom on the boundary. So it's the entanglement between two boundary regions, a region and its complement. Again, you compute the secondary entropy as a measure. Same type of approximation to make the calculation possible. Randomization in each spin sector over the vertex wave functions and large spin approximation. Again, you can map to an easy model. And the problem becomes, once more, to a minimization problem of the energy for the easy model. In the homogeneous case, all the spin network spins equal. You have a certain Hamiltonian in which you realize that there is an additional contribution to the Hamiltonian that is basically measuring the bulk entropy. Even though you're only looking at data on the boundary, because this is the boundary of a graph and there is some indirect talking to each other of boundary degrees of freedom, that gives an additional contribution to the Hamiltonian. Now, if this contribution is vanishing, what we get is exactly a Ruta Kanayagi area law in which the entropy is proportional to the size of a minimal surface separating the two boundaries through the bulk, the two portions of the boundary through the bulk. And the size of such surface is just the number of links crossing it. It's a purely combinatorial notion, and this is not strange because you fix the spin, first of all, and then you also fix them equal. So they only give you a proportionality factor here. If already in this simple case, however, if the bulk entropy, the contribution from the intertwiners correlations across vertices, between vertices is non-vanishing but small, then you get a bulk correction to this Ruta Kanayagi area law. And you can define the entropy correction also in the case in which there is a larger intertwiner entropy. things become even more interesting, and I'm using my last minute, I think.
Please, there is some
Morally.
more.
In the inhomogeneous case, when you have different but fixed spins of the original state, spin network state, again, you can map to an easy model, but it's now an easy model with inhomogeneous couplings. Then you can still write down the Hamiltonian in terms of some uniform rescaled temperature, but again, different couplings. And you again have to minimize this Hamiltonian. Now, in the case in which the bulk intertwiner contribution is again vanishing, we find the Ruta Kanayagi area law as before, but very interestingly, now you find a minimal surface, but the surface area now takes correctly into account the fact that you have both spin degrees of freedom and combinatorial degrees of freedom, exactly as you would compute the area from simplicial geometry, with the spectrum for each surface, and then you count, then you sum the surfaces, associated to each link. And then when you have a non-zero intertwiner entropy, something interesting happens, that you get a bulk contribution to the area law, fine, but quite intriguingly, the larger the entropy of the bulk region you are considering is, the less is convenient for the minimal surface to enter that region. In the limit in which you take a region in the bulk and that has a large number of quantum correlations, the area, the minimal surface just cannot enter at all that region. And if you take more and more on the boundary, in the limit, you would take all the boundary into consideration. The Ruta Kanayagi surface is in fact the boundary of that region. This is exactly what you would expect from a black hole, and from a situation in which the Ruta Kanayagi formula coincides with the Bekenstein entropy formula. Anyway, I close it here. These are again the conclusions. I've shown you 4 main things. One is that quantum gravity states can be understood technically as tensor networks, so as containing and based on the entanglement properties between the fundamental building blocks. I've shown you that this allows to already draw an entanglement geometry correspondence at the level of simplicial quantum geometry. I discussed how the same quantum gravity states can be understood, recast as defining bulk boundary maps, and how you can identify conditions for such maps being isometric as a sort of a preliminary necessary condition for being holographic. Last, I told you about the derivation of a Ruta Kanayagi formula for spin networks, including bulk corrections, with some intriguing hints to possible black hole-like configurations, which I have to admit I don't fully understand. And this is the outlook, just to say that there is a lot of ways in which what we've done so far can and should be improved. Thank you.
Thank you. So questions, any comment? Please, Vincent, Riverso.
I have not completely understood why your Kanayagi law reduces to
well,
in the case of black hole.
So if you're asking for the why in the sense of what is actually going on in the states, I don't fully understand it. It's just that somehow the correlations in the bulk are sort of adding so much to the energy of the effective easing model that if you were to include that region, the entropy cannot be maximized, or the energy of the effective easing model minimized. It just prevents you from going lower and lower. but I don't fully understand how that works. If you're asking why we interpret it as the Bekenstein-Hawking entropy law, is because it is that when the moment you take the boundary to be the full boundary in the limit in which you take one region to go into zero and the other occupying the whole boundary, and the bulk entropy growing larger, you see that the minimal Ruta Kanayagi surface it coincides with the boundary of that bulk region. And then you have a region with an entropy associated to the bulk, to the boundary of that region, which basically doesn't talk to the boundary. From the boundary, you don't have access to that region, in other words. And that's basically what would happen in Bekenstein-Hawking entropy for a black hole. But for now, it's more of an analogy than more.
So I would like to thank all the speakers of the session, and I know there are no other questions online, so thank you also to you, Daniele. So this closes the session.